So here's a problem that comes from last time, and it's been a while, so let's go through it. Solve using an augmented matrix. So I want to remind ourselves what we mean by these things. So first off, we'll start with what is an augmented matrix? Well, the idea for augmented matrix is to say, let's just store this in a much more compact form. And so instead of writing down all the variables, we say what really matters is the coefficients. What are the numbers? So you say, okay, we have two variables. So there's sort of an x1 column. And so you write down the coefficients. Then there's an x2 column. You write down the coefficients. Then the equals, it becomes this dividing line. And then finally, there's the constants on the other side. Now, of course, if you're going to do this, make sure you have everything lined up. You want to make sure that everything in the column associated with what the variable is the same, right? So if they had x in 5x2 plus 3x1, we want to be careful. Well, hopefully no one's that sneaky to us, but we pay attention. We pay attention. All right, so that's what an augmented matrix is. But now the question, what does it mean to solve? In particular, solve using an augmented matrix. So, when we think of a solution to our system, what would it tend to look like? So, looking ahead, we can think about what we want. We want to say that x1 equals some number a, and x2 equals some number b. In other words, we know exactly what x1 is and exactly what x2 is. That's the solution we're shooting for. So that's what we want. So now we say, okay, what does this look like in terms of an augmented matrix? Well, what's the first column? What are the numbers? Well, it's the coefficients. So here, what's in front of the x1 is 1. You might say, but Steve, there's a problem. There is no x1 in the second equation. There is. There's always a hidden x1 called 0x1. And so, you put a 0. And similar, you can say, look, it's 0x2 and 1x2 ab. So, this is what a solution looks like. So what we're going to do is we're going to figure out how do we take this left-hand side. We want to make this part look like 1, 0, 0, 1. That's our goal. So when we talk about solving using an augmented matrix, we're saying we're going to make the part on the left of the divider line look like this very special set of this arrangement. We'll give it a name in the very near future. But let's just call it nice. We want it to look nice. All right, so that's our goal. Now, what are we allowed to do? Well, we can only do things that would make sense to do with the equations. And so in particular, we can't do things with the columns, but we can do things with the rows. So we have a few things at our disposal. We can scale, we can swap, and we can add a multiple of one row to another. And so now we get to go on a sort of a choose your own adventure. How do we get from the left-hand side looking as it currently looks to the left-hand side looking like what we want it to look like? Okay. Well, even though we can't do anything with the columns, there's a good school of thought we're going to get into today, which says, well, let's just work one column at a time. So I'm going to say, well, let's focus on the first column. We know what we want the first column to look like. So we say, all right, let's make it look like that. And we'll start up here. Well, currently there's a 2. We don't want a 2. We want a 1. How can we make this 2 into a 1? We could divide by 2, yeah. So we can scale. And so I think the book uses the notation, if you take 1/2 the first row, that becomes the first row. So 1, -3/2, 4. And we haven't done anything with the second row. That just comes along for the right. All right, good. So that's progress. We kind of said like, good, we've got this 1. Woohoo! Put a little check mark there. And hopefully we keep that check mark there. We don't want to lose it. Say, all right, now that we have our 1, let's work on making the next entry, this 5, into a 0. Oh, I see a question. You're right. I don't know why I did that. -8, this should be +1, -4 and +1. Thank you. Thank you. All right. So, how do we make this 5 into a 0? Well, we can't multiply a row by 0. Because that says, haha, ignore this equation. Like, no. We can't ignore the equation. We need to keep that information. We don't want to lose information. Okay, so scaling is out. Swapping won't help us. So we have the sort of the most powerful rule, which is also the least obvious rule. So that's why we have to practice it more, which says you can add a multiple of one row to another row. So this is essentially the idea of elimination. When we talk about elimination, it's adding a multiple of one row to another row. So in particular, we say, well, I want to do something. I'm going to keep the first row as is, because I like the first row, assuming I copied it correctly. And now I say, well, I'm going to use the 1. I'm going to use this 1 to knock out the 5. So I want to cancel that 5. So what we can do is we say, well, let's take -5 times row 1, add that to row 2. That becomes our new row 2. So that's the notation the book would have. -5 R1 plus R2 is now R2. So we don't say it equals R2, it becomes R2, it replaces R2. And if we do that, okay, so you have to multiply -5 times every entry in the row and add down. -5 plus 5, 0. By design. That's why we chose to do what we did. Everything else along the way is now going to be like, but that's okay, we're patient. -5 times -3/2. Well, 2 negatives make a positive, so that's at least some good news. That would be 15/2. Now, if I take 15/2 and I add 3, so we can do we're allowed to do computation on the side. -3/2 times -5 plus 3, right? -5 times the first row plus the second row. I'm just doing that entry. So it's 15/2 plus 3. What does 15/2 plus 3 become? Common denominator is 2. 15/2 plus 6/2. 21/2. Yes, fractions can occur. We're not going to be worried about them or overly nervous. We'll do our best. We'll do our best to keep our nerves calm. The last entry, -4 times -5, 20. Add 1, 21. Okay, so our success continues. We've gotten that 0. Woohoo! Nice! All right. Now we're like, the first column is looking pretty snazzy, which means we're ready for the second column. So now we're ready to move to column 2. So as we look at column 2, we say, well, we're going to have to make this entry a 0, this -3/2, and this 21/1/2 entry a 1. And what I'd recommend is make what you need to make into a 1 first. So what do we need to do to make this 21 halves a 1? Think what we started by doing. We started by scaling. It's an idea so nice, we'll do it twice, right? So we're going to scale row 2. Now here's the really cool thing. You might say, well, won't that affect this part? No. Because when you scale 0, you get 0. It's almost like they want it to happen that way. And that's because they want it to happen that way. All right. So we're scaling by the reciprocal. So if it's 21 halves, the reciprocal is 2 over 21. So at this stage, we get 1 minus 3 halves minus 4, because the first row, nothing happened to it. The second row gets scaled. 0, 1. Now, if I take, right, it's 1 by design. It has to be 1. 21 times 2 over 21 becomes 2. All right. Notice we kept the first column pristine. Are we done? No. But we're 3/4 the way done. What's left? This last entry. Got to make that a 0. All right, so how can we make that last entry a 0? This little negative 3 halves. What can we do? What can we do? Well, what can't we do? We can't scale. That's out. Because you can't make a 0 by scaling. You can't swap, because I would put a 1 there. So it means elimination. Now, that only row available to us is that second row. So we have to add some multiple of the second row to the first row to knock out the negative 3 halves. So what multiple do we need to use? Well, what times 1 plus negative 3 halves gives us 0? The answer is 3 halves. So we take 3 halves times the second row plus the first row. That's to become our new first row. The second row stays as is, because we're not changing the second row. In the first row, well, we're going to get 0 plus 1. So that's 1. Then we're going to get 3 halves and a negative 3 halves. That's 0. Then we're going to get 3 halves times 2, which is 3, plus negative 4, which makes a minus 1. And then we've gotten our 0. Now, notice, as we were doing the second column, we made choices that said, we're not going to affect the first column. We like the first column. We worked hard to get it. So let's be careful that as we work on the second column, we keep the first column in the same form. Now, we're ready to read off our answer. So, according to this, what is x1 and what is x2? x1 is negative 1. x2 is 2. Is there any way that we can check our answer without redoing the work? Plug it in. All right, let's see if it works. 2 times minus 1 is minus 2. Minus 3 times 2 is minus 6. Minus 2 minus 6 is minus 8. 5 times minus 1 is minus 5. 3 times 2 is plus 6. Minus 5 plus 6 is positive 1. So, yeah, we definitely got the right answer. Woohoo! Smiley face us. We worked hard. All right, so any questions on that? Now, if you feel good about that, great news. That's what we're doing today, except bigger. So we're going to go up a step. All right. So that's why we took our time. That's why we took our time. Well, quick thought for the day from a famous boxer, Muhammad Ali. I hated every minute of training, but I said, don't quit. Suffer now and live the rest of your life as a champion. I think people probably have a similar view of math classes. I'm not the biggest fan of the math class. I hope you don't say I hated every minute of math class. But don't quit. Keep at it. Pay the price now so that you have the tools, the skills that will carry you for the rest of your life. It's worth the investment. Now, what's our goal for today? We're going to talk about the idea of reduced matrices. In essence, reduced matrices is, what are we shooting for? When we're doing this process where we're using augmented matrices, what's our target to end up with? And then we're going to talk about the idea of Gauss-Jordan elimination. Now, Gauss and Jordan were two different mathematicians. Gauss, by the way, is often considered one of the great mathematicians. And what did they care about this? Well, used to be, we didn't have computers. And so you'd have to do all this work by hand. And the goal was to say, can I find a nice, quick, systematic way to solve systems of equations? Because they often, frequently arise in various contexts. And so they had motivation. Let's find a fast way to do it. So that's why their name is attached to it. Okay, so as a reminder, we have our 3 row operations that we've been talking about. We can swap rows, we can scale rows, we can add a multiple of one row to another. Ultimately, our goal is always the same. Simplify. Make things as simple as possible. That's what math is. Algebra is just a series of, can I simplify things to the point where I say, I simplified it so much I can just read off the answer. Now, using the row operations, I said we have a target, and that's the reduced form. So what does reduced form say? It says, well, I want to make sure that when I look at what's at the end process, a few things are true. For any row which is not all zeros, the first entry is a 1. Now, that's not hard to achieve. We can always scale so that the first entry is a 1. And it says, okay, once you have that first entry as a 1, that particular column, everything else is going to be gone. Everything else is going to be zeros. All right. We can do that by doing elimination. Now, the other thing is that we want to arrange the rows. So this is now the swapping. So this bullet point is achieved by scaling to make the first entry 1, and then using that first entry to knock out everything else. So it's the last 2 row operations. The other bullet point here says, I'm going to sort the rows. And I'm going to sort the rows that when I look at the first ones, they move from left to right. Now, it might happen that we don't use, that not every column gets a leading 1. There's a fancy term called pivots if you talk to your friends taking linear algebra courses. But the important thing is they go from left to right. If we have any row with all zeros, that's at the bottom. So any row without a non-zeros at the bottom. So that's reduced form. And the thing is that once you get to reduced form, you can read off your answer. Just like we did with the previous problem. That's what we want to do. Any questions? All right, let's try some things. Here are 4 matrices. They are not in reduced form. There's something wrong with every single one of them. But each one can, with one single row operation, be put into reduced form. So what's the row operation that needs to be done? And then what's the reduced form of the matrix? All right, let's start with this left one. What's wrong with this augmented matrix where it says 1, 0, 2 in the first row, 0, 3, negative 6 in the second row? What's wrong? Yeah, this row has a non-zero, and the first entry is not a 1. So that's the problem. That's the issue. So we need to fix that. So how do we fix the first entry not being a 1? Yeah, we can divide by 3 or scale by 1/3. So this is the row operation we need is to scale the second row. So we're going to take 1/3 times the second row, and that becomes the second row. The other rows stay as is, so the first row still stays 1, 0, 2. The second row, divide everything by 3, 0, 1, minus 2. All right, good, good. Now, let's go to the second one. So we have 1, 5, 4, 3, 0, 1, 2, minus 1, 0, 0, 0, 0. This is not reduced form. What's wrong? This one's a little bit more subtle. What do we need? Well, it's not. We do need something to be 0. What needs to be 0 that's not currently 0? It's this entry here. That's the entry which is bad. Why is it bad? So it says first non-zero entry is a 1. Now that's true for both rows. Like this starts with a 1. Here's the first non-zero entry. That's a 1. But then it says in the column with that 1, all other entries are 0. So in the first column, great. But here, in this column, that 5 is not a 0. So it's not in the reduced form. So our goal is to knock out that 5. What can knock out a 5? Or perhaps I might very suggestively say, what can help us eliminate that 5? Whoa, elimination. What can we do? What can we do?
Multiply row 2 of negative 5 and then add 2.
Yes! Yes! Brilliant! Minus 5 times row 2 plus row 1. So we're using the 1 to knock out the other entries in that column. That's the goal. So we have the 1, we just need to use it to knock out the 5. And that's going to become our new row 1. By design, it won't hurt this column, which has that leading 1 and zeros, because there's a 0 here. So that helps protect that column. So the second row and the third row stay the same, because it's only that first row that's being affected. 0 plus 1 is 1. Negative 5 plus 5, 0. Now the harder work. So it's going to become negative 10 plus 4, which is negative 6. All right, negative 5 times 2 plus 4. And then negative 5 times negative 1 is a positive 5 plus 3, which becomes 8. All right. Now let's get to our third one. We have 0, 1, 0, negative 3 in the first row, 1, 0, 0, 0 in the second row, 0, 0, 1, 2 in the third row. This is not in reduced form yet. What's wrong? How do we fix it? As a reminder, here's reduced form. The first non-zero entry is a 1, check. In the column without 1, all the other entries are 0, check. So it's not the first bullet point, so it's the second bullet point. What's going on? Where's the first one? In the second, then the first, and the third. We're not moving. The first one should be going from left to right. That's not what's happening. We're just we're doing a little bit of a zag, or maybe we're doing a zig. We want to be consistent. So, how do we fix this problem? In one step. There's ways to do it in not one step, which are very like, what were you thinking? But in one step, one stroke of the pen, how do you solve it? Yeah, just swap. And so that just says, I'm swapping row 2 with row 1, or row 1 with row 2, however you want to write it. So the third row stays in place, it's not being affected. The first row moves to the second row, and the second row moves to the first row. All right, last one. We have the matrix 1, 2, 0, 3, 0, 0, 0, 0, 0, 0, 1, 4. This is not in reduced form, but we're one step away. What's wrong, and how do we fix it? There's this note here that might be very suggestive. What's wrong? Yeah, you have this row with all zeros. That should be at the bottom. So we're like, oh, we need to again do a row swap. So it's true that in terms of the ones, they're going from left to right, but this has all zeros, so that should always be at the bottom. So we're doing a row swap, row 2, row 3. First row stays where it is. Second row is now what was previously the third row, and the third row is what was previously the second row. All right. There we go. There we go. Before we leave this, I want to talk a little bit about reading off the answers. So for this one, let's assume our variables are x1, x2, x3. For this first one, what does our answer look like? X1 is 2, x2 is negative 2. So it's like you're reading off the column on the right-hand side. That's a reasonable way to think about it. Let me skip to the third one. And the reason I'm skipping to the third one is because in these two, you get a very nice arrangement where you essentially have a square with ones down what we call the diagonal. So here we have three variables, x1, x2, x3. What's x1? 0. x2? Negative 3. x3? 2. It's the column. So once you get it down into this nice reduced form, the column is the answer. Well, let's talk about these two. They are slightly different. You notice here, we have, in this situation where you have a column, where you have a non-zero entry which is not a leading one. Now, what does that tell us? Well, essentially it tells us that there's a free choice. And if we write it down, there's two ways to think about this. Let me write it down, first off, literally what the equations say. It says x1 plus 2x2 equals 3. That's the first row. And the third row says x3 equals 4. And the last row says 0 equals 0. Now, don't worry, 0 is always equal to 0. Because of that, we oftentimes skip writing it down. So what does this say about what solutions we have? Well, we know for sure that x3 equals 4. But then we say we get a choice. Any choice of x1 and x2 that this is true works. Now here's what we do in practice though. What we're going to do in practice is we're going to take this column and we're going to think of this as sort of like a free choice. So we're going to think of any column where we have a non-zero entry which is not a leading one. That's a free choice. And so we're going to give it a name. So we tend to use symbols like S and T. So I'm going to call it like S for a second. So this becomes x1 plus 2s equals 3, and x3 equals 4. So that our solutions look like x1 is 3 minus 2s, and x3 is 4. But that's one way to think about it. You might say, well, what is x2? X2 is that free choice. So you have these sort of like options. Now you might say, is that good? Well, maybe. But you can think about now, how do I interpret it? And we're going to get into some examples of this next time. If we do that here, what would we get? Well, I'm going to think of, we have this column here. So we're going to think of x3 is a free choice. I'll call it T. This is a free choice. I can make it be whatever I want. Then I get x1 minus 6x3, which is T, equals 8. x2 plus 2x3, which I'm going to think of as T, is negative 1. And then we had our x3, our free choice, is T. Or x1 is 8 plus 6t, x2 is minus 1 minus 2t, and x3 is t. So now we say, okay, pick t. And there might be some other constraints coming into play. All right. But we want to make sure we can read off the solutions. All right. Well, I'm sorry, I pulled that away really quickly. Are there any questions? Being a little bit vague, but we'll get into some word problems next time, where we talk about how we use this when we don't necessarily have like a unique solution, but we have a range of solutions. Like, okay, then what do we do with that information? All right. Well, so somewhat systematically, we're going to talk about the idea of Gauss-Jordan elimination, and we've been doing it. So what's the process? The process is we want to make it look like reduced form. How do we do it? Well, you know, channel your inner Lord of the Rings character. Column, column, right? You work column by column. And so you say, let me just scan. Let me look for my first column with a non-zero entry that I haven't done anything to yet. Okay, so you scan, you find your first column with a non-zero entry, say, beautiful. I'm going to put that near the top. I can swap it up. Now, if I've done something with a previous column, I lock those in place. So I'm going to do it, you know, this recursively. But I'm looking for the next one to work on. So I find that. I say, okay, there's my non-zero entry. Move it up as high as I can, and scale it to make it a 1. Now I have my 1, and it's in the right place. Knock out all the other non-zero entries in that column. And what's going to happen? Well, once you do that, you might say, well, wait, won't that affect the columns that came before it? And the answer is no. Because if you think about what's in front of that first one that you just created, the answer is all zeros. So when you use elimination to knock things out, you're not affecting anything before that entry. So you won't hurt what you've done before. So you don't want to do work and then undo it by making more non-zero entries. Our goal is we want more zero entries. Once we've knocked out, we say, great, we like what we have, repeat. Repeat, 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 until there's nothing left to do. All right. So if nothing else, just remember, work column by column, and you'll be okay. There's a generic rule of thumb. If you have more variables than equations, we usually have lots of solutions. That's where we get free choices. If we have more equations than variables, we tend to get no solutions, but there are exceptions, so be careful. All right. Well, how much time do we have left? Plenty of time to do one example. Let's see if we can do progress here. Solve the following by Gauss-Jordan elimination. And by the way, computers love this. Computers love solving linear systems of equations. If anything, computers are designed to work with matrices. They're big matrix machines. You may have heard of companies like NVIDIA, who are worth a lot of money now. And what have they done? They've made a really good matrix manipulator. And so we're going to channel our inner computer. But one nice thing is we're a little bit smarter than a computer, and so we can use that to our advantage sometimes. But all right, here we go. Solve the following by Gauss-Jordan elimination. And so we're going to do this in augmented matrices. So step one, let's turn this into an augmented matrix. So we have our columns. For each variable, we get a column of numbers which are our coefficients, 3, 1, negative 2. In the next column, 1, negative 2, negative 1. The last column, 2, 1, negative 3, equals 2, 3, 3. Now, in essence, all we're doing when we put it into this augmented form is just rewriting in sort of a compact notation. Everything could be done without putting it into augmented form. This just helps us keep track of things more systematically. All right, so our goal was work column by column. So we start with the first column. We say, all right, is there any non-zero numbers in that column? Yes, there's lots of non-zero numbers, plenty of them. What do we want? Well, we want to make this column look like 1, 0, 0. That's our goal for that column. So we have to decide how to get there. We must choose. There's some freedom you have. So what would you like to do? I'm not claiming that there's a wrong choice. Well, yes, there are wrong choices. I should say, I'm not claiming that there's a single right choice. But there are right choices which will make things easier. The fact that we have a 1 here is going to be helpful. So you don't have to make a 1, we just have to move it. So let's take advantage of the fact that they gave us a 1 by swapping the rows. Do you want me to keep running down the row operations as we go through? Is that helpful? Okay. So this says swap row 1 with row 2. Row 1 swaps with row 2. So we get 1, negative 2, 1, 3, 3, 1, 2, 2, minus 2, minus 1, minus 3, 3. All right, so the 1 is in the right place. Now we need to knock things out. So we knock things out by using the first row and combining it with the other row. So in other words, we're going to add a multiple of the first row, where that one is, to knock out the other non-zero entries. So how much do I have to multiply the first row? So when I add it to the second row, I knock out the 3. -3. So -3 times the first row plus the second row now becomes the new second row. All right, so we'll do this a little bit slowly. That says we're not changing the first row. Whoops, I gotta be careful there. Part of the challenge with this problem is, I can already see I messed up. I put a -2 down here. It should be a +2. 2 minus 1 minus 3. Sorry about that. So the second row, -3 plus 3 is 0. -6 plus 1 is 7. -3 plus 2 is a -1. And -9 plus 2 is -7. Sorry, what? Which one? Oh, that's a -2. Oh my gosh, why did I do that to myself? You're never going to believe that I actually have a degree in math. I do, I promise. I really did study math. Okay, -3 minus 2 makes -5. There we go. Ha 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 ha. Thank you. All right. Well, we're going to have some interesting numbers. All right, we still need to knock out this 2. So what can we do? Well, add -2 times the first row. Add it to the third row. That becomes our new third row. So, first 2 rows stay as is. 0, 7, -5, -7. Now, -2 plus 2, 0. Then -2 times -2 is 4. Plus a -1 makes 3. -2 times 1 is -2. Plus -3 makes -5. Then you have -6 plus 3. And that makes -3. All right. Well, interesting times ahead. Now what? Well, good news is first column. We're happy. So, if we're happy with the first column, what should we do? Go to the second column. Now, when we're looking for non-zero entries, I don't want to look here in the first row because I already have the first row spoken for. So I'm looking in the other rows. So I come here and say, do I see some non-zero entries? Yes. All right. Since I see non-zero entries, we need to do something. Well, we need, in particular, our goal for the column as a whole is going to be, we want this to look like 1, 0, 1. So one of these needs to be a 1, and we need to put that 1 in the second slot. It looks like right now fractions are not avoidable, so we'll just bite the bullet. Let's scale the second row by 1/7. So if we do this, we'll have that 1/7 times row 2 is our new row 2. So our first and third rows stay the same. So we still have the 1 minus 2, 1, 3 in the first row, and the 0, 3, -5, -3 in the second row. But the third row. The second row becomes 0, 1, -5/7, and -1. All right. Now, that 1 that we created, we're going to use that 1 to knock stuff out. We want to knock out everything else in that column. So that -2 in the first row, second entry, and that +3 in the third row, second entry, we want them gone. So we're going to think of ways to combine, to eliminate them. All right, so let's start with the negative 2. What do we do? How do we use this one to knock out the negative 2? Well, multiply middle row by 2 and add it to the first row. So we're going to take 2. Sorry, I'm just going to add a little divider here. 2 row 1. Sorry, row 2. 2 row 2 plus row 1 becomes our new row 1. So our middle row, 0, 1, negative 5 sevenths, negative 1, and our bottom row is 0, 3, negative 5, negative 3, stay as is. The top row will become 0 plus 1, 1. That first column is protected. 2 minus 2, 0. Good, we're making that second column look good. Then we have to do some numbers. Negative 10 sevenths plus 1. Well, negative 10 sevenths plus 1 is negative 10 sevenths plus 7 sevenths. So that would make it negative 3 sevenths. So that's our 2 row 2 plus row 1. Negative 2 plus 3, 1. All right. We still need to knock out another entry. So we need to knock out that 3. So, similar way, we're going to take negative 3 row 2, add it to row 3. That leaves the first 2 rows the same. The last row becomes 0. Negative 3 plus 3 makes 0. 15 sevenths minus 5. Well, what will that be? Well, minus 5 is minus 15. Sorry. Okay, I shouldn't do this in my head. So we have 15 sevenths minus, all right, negative 3 times negative 5 sevenths is 15 over 7. And then we're going to add negative 5. Now, what is 5? Well, if we multiply it by 7 over 7, that's 35 sevenths. So we get negative 20 over 7. So we get negative 20 sevenths. On the other hand, we're going to get minus 3 times minus 1, which is plus 3. And then we add to the negative 3, which gives us 0. All right. Now, we've succeeded with column 1. We've succeeded with column 2. We now come to column 3. We're looking for a non-zero entry. We're not going to touch the first 2 rows. So we say, okay, do we see a non-zero entry? Yes. So that's where we're going to work next. And our goal is for this column, we want to end up with this column being 0, 0, 1. Well, no surprise, we're going to scale. So we'll take negative 7/20 times row 3 becomes the new row 3. And if we do that, we get the following. The first 2 rows stay the same. The last row becomes 0, 0, 1, 0. All right. Well, I see we're short on time, so I'm just going to go ahead and say what needs to happen. We need to knock terms out. So if you take, we'll do them simultaneously. So we're going to take row 3, times it by 5 sevenths and add it to row 2. That becomes the new row 2. And we're going to do a similar thing. 3 sevenths times row 3 plus row 1 becomes the new row 1. And if we do that, the first 2 columns are safe. The third column, we're going to knock out those entries. What happens with this last piece? Well, we get 0 plus negative 1, which becomes negative 1. And then we get 0 plus 1, which becomes 1. So what's our solution? X equals 1, y equals 1. Sorry, y equals negative 1. Make it more clear, negative 1, and c equals 0. And there we go. Ha! Straightforward, right? Great. All right, we'll do more practice next time.